Okay, so I'm not going to play any sound here. I'm just going to talk about this. This is where we finished Monday's class, the idea of synchronous AC motors. So the idea here was that we went through a pretty lengthy discussion about three-phase power and then how this translates to coil energization in a three-phase motor, and then how this creates. We showed a very simplified case where you had a single pole corresponding, just two poles north and south, each corresponding to each. So a single coil for each phase. This is what an actual AC synchronous motor would look like, where now instead of just having three poles, pairs of poles, we have a multitude of them. And that's going to create north and south poles around the stator, and these north and south poles are going to rotate given how they are driven with AC power. So just to kind of show this video here, this is showing that the rotor's not moving right now for a second, but this is showing how the stator field is continually rotating. And this rotational speed is directly tied to the power at the wall, right? So you have this big industrial machine that's plugged into three-phase power, directly tied to that. And what's nice about this type of system is that the frequency of the power at your wall is actually pretty stable, right? So you can directly use this variable power source to drive a system at a set the end of the class with on what's today? Wednesday? So Monday, looking at just a motor spec sheet here. This is Baldor, which is a gigantic motor company, but they sell AC synchronous motors for three-phase power systems, and use motors in 900 RPMs, 1200 RPMs, 1800, 1360 RPMs, and that's based purely on the number of poles per phase. Right, so if you only had two poles per phase, which is the case that we had when motors in a spin at 3600 RPMs, and if you have more poles, say 4, 6, 8, like we showed in the video where you had a bunch of poles in your system, it's going to spin slower. Okay. And so what's nice about this is you don't have to have all these fancy motor controls, etc. It will spin at that speed. Now, you don't have any real control over this once it's already spinning at that speed, at least not much control over it. So it would have to be an application where you do want constant speed from your system. You can then use gearboxes. Say you don't want to spin at 3600 RPMs, you can use gearboxes to then have it spin at the speed you want, right, to gear this rotation here. All right, so AC synchronous motors, we're not going to talk about too much besides what we talked about thus far. But this is a solution that is in industry everywhere. Okay, so if you go into any factory, they're going to have, I don't know, I'm going to guess, if it's a factory, hundreds of AC synchronous motors running. Okay. Compressors, like compressors for air conditioning systems, systems in your house, those use AC synchronous motors because oftentimes they don't really care about too much ability to tune them. They just want it to spin at a constant rate. They'll use AC synchronous motors. They're a very common solution. All right, because they're simple. They're not necessarily simple in architecture, but they're simple in the way they operate. Okay. Pull up something really quick. Okay. So just kind of some notes to fill this out. Just for your own personal notes. So number of poles. Fixed by motor design. An inexpensive way to have controlled motor speed. And then one thing I forgot to mention, there are some, yes?
Is it inexpensive or expensive? Because your notes on like your filled out notes say expensive.
It should be inexpensive, yeah. Okay. Oh, I see what's going on here. Okay. So inexpensive way to control motor speed. There also are more fancy, I guess, sophisticated ways of doing this as well. There are variable frequency drives. Control frequency of the three phases. Okay, so if you just use the wall power as is, it's going to be oscillating at 60 hertz because that's what we use in the US. There are examples which use variable frequency drives to get the same sort of behavior, but then in terms of having synchronous actuation, but then you have the ability to change speed. So here's an example from, this is a Honda Accord hybrid motor. So this, you can see the stator coils here are packed to the gills, basically a lot of different poles. But then you have permanent magnets on the rotor. But this would be an example of which you have a synchronous AC motor, but the background electronics, it's not, obviously a car's not plugged into your wall. That's a given. They have frequency drives. They can be continually changing the frequency of these three phases to then get this motor to spin at the speed that they want for it to drive a car so that your car can go at the speed that they want it to go. Okay, so there are expensive ways of using this similar solution. Toyota Prius uses a permanent magnet synchronous AC motor as well, but here's a good example from the Honda Accord. All right, so these are, systems like this are used all the time. I don't know if you've ever, probably if you've driven enough Lyft rides or Uber rides, you've probably been in a Toyota Prius before. Right? Okay, so AC induction motors. This I'm largely going to have just a video talk about this. So AC induction motors, they overcome the issues of AC synchronous motors not being self-starting. So we didn't cover this. We didn't go through that part of the video. It's not a major part of our discussion on AC synchronous motors, but AC synchronous motors won't just start on their own. They actually have to have mechanisms to help them start. But AC induction motors will start on their own. Okay, so I'll show the video of the AC induction motor here. I think it's much more instructive than anything I can do with going through steps in class. Okay, so why isn't the volume working? way up. Ah, there we go.
In this video, we will learn the working of a three-phase induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame.
Okay, so very much, I think you're going to see some common elements here, right? This will look very much like the DC motors that we talked about. Also, the AC synchronous motors would look like this as well, in terms of their stator currents.
Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field.
Yeah, so just like we talked about on
To
Monday.
understand this phenomenon much better, consider a simplified three-phase winding with just three coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these three positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in the magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating.
So to note,
A similar phenomenon.
I think these videos I find to be very good, but I think they were, there's a translation issue here.
So this situation has become like a current-carrying loop is situated in the magnetic field. This will produce magnetic force in loop, according to Lorentz.
Okay, so Lorentz, that's not Lorentz, it's Lorentz law. Just so there's no confusion there. There's a few cases where they drop certain articles of English that I think lost in translation.
So the loop will start rotating. A similar phenomenon had an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current.
Okay, so when they say squirrel cage, they're assuming that you know what a squirrel cage is. It's not a device to trap squirrels. It's basically this arrangement. So they're given this example of a single wire inside of this rotating magnetic field. So now this is the case, as you can see, these are all connected. So the rotor, like every other case we either had rotors that are composed of coils, electromagnetic, or a coil for electromagnet, or they were permanent magnets on the rotors. This is considerably more simple than all that. This is just a cage-like structure, and it's made of some sort of electrically conducting material. That's it. That's all there is to it. And so then you have the ability to then form loops, such that you have current to flow into this one, and then say out this one. Right? So you're just creating this conduits for current to flow, and it's going to be flowed back because of back EMF and Faraday's law, and you're going to get force from Lorentz law.
Current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating, But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So there won't be any induced EMF and current. This means zero force on rotor bars. So the rotors will gradually slow down. But as it slows down, rotor loops will experience a very magnetic field. So induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor.
Yeah, so this is getting then into kind of the details of the mechanical transmission. But that's the basic function of induction motors. We're not going to spend too much time besides this short, brief introduction to these. Examples of where you'll see this. So here is the Tesla motor that's in the Model S. Okay, so this uses induction motors. This is one that's intentionally open so you can see what's going on inside. But here you can see. Let me zoom in here. So you can see these are very expensive, very efficient motors that are used here. Here you can see this is a cross section. This has been cut. This is where your field coil has been cut here. And then on the inside here, this is your rotor. Looks like it's really smooth. It's basically this squirrel cage with all these different laminate sheets stacked in it. But inside there, you'd have the induction coils. Right? So the arguments I've heard of why Tesla uses AC induction motors is because they were worried about sourcing of permanent magnets for their motors. So if you look at the case with this Honda Accord and what's also used in the Prius, this uses permanent magnets. I mentioned this briefly before about permanent magnets are fairly expensive. They're very, very, very efficient, but you have issues with the location in which you get the permanent magnets. There's not really a good domestic source, and so there's worries about our primary source being a country that we're not always friendly with, I guess. And so in terms of having basically a supply chain that's stable and you always can rely on, they went with this induction type motor, which you look at the components of this, it's basically coiled wire, copper, not an issue there, other types of ferrous materials, and that's about it, right? So in terms of sourcing that's something that we do with hundreds of industries in the United States all the time, right? So they went with the AC induction motor with this one. But the Model 3 is back to using permanent magnets. So I don't know, I'm not sure what the rationale was for that, why they have different ones, but they have different motors for different product lines. Last one to talk about before we kind of end this discussion, stepper motors. Who's used a stepper motor in some sort of project before? Class project, internships, a few people? Okay, so stepper motors are nice in that when you as the engineer who purchases them, they are very, very easy to use. Because and we'll talk about the stepper motor in a second in terms of more detail in terms of how they function, but they basically have a lot of sophisticated electronics that make it really easy to use. So I'll show an example of this in a second. Maybe it makes sense to just go to the example right now. So stepper motors. Thought I had a video of this. I used to have a video. I used to have a GIF of this.
Did they just put CPs in their software? Genius.
I found another induction point. How does a robotic arm in a manufacturing facility repeat the exact same movements over and over? How does an automated milling machine move with such precision? It's all because of the stepper motor. What's special about the stepper motor is
That's exaggerating a little bit. A lot of robots do not use stepper motors, but okay. It's not all because of the stepper motor.
motor without a closed feedback loop. It is a simple, accurate, and open loop system. Let's first understand how the variable reluctance type of stepper motor works, which is the simplest one. Later on, we will move to a highly accurate and commonly used motor type. This motor has 6 stator teeth and can be energized with 3 separate DC power sources. The rotor is made of a stack of steel laminations. It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. You can explain how this stepper motor works by yourself. If you de-energize coil A and energize B, it becomes clear that the rotor will rotate as shown from the G.
Okay, so just to note, in terms of function here, this actually behaves much more like the moving iron transducers or solenoids than all the other motors that we've seen before. Okay, so it's looking to minimize the reluctance between this air gap here. Okay, so if we go back a step here, when this coil was energized, this is the way in which we minimize the air gap. Then this one's turned off, and then B is turned on. And therefore, to minimize this reluctance, this system rotates this tooth of the rotor into place, and then this one rotates in place as well. So it's actually a lot more like a solenoid than other motors.
If you de-energize coil A and energize B, it becomes clear that the rotor will rotate as shown. From the geometry, it is clear that the one-step size is 30 degrees. To get the next step, de-energize coil B and energize C.
Okay, so I hope it's clear why it's called a stepper motor, because as you fire these different coils, you are stepping in rotation. So A, B, C, A, B, C, right? If you ever wanted to go back, say this is in configuration it's aligned with C, if you ever wanted to go in reverse, you would then energize B, right? So you could step back and forth with this type of motor.
Coil A becomes energized again. In short, the rotor moves to the position with the least reluctance. The step size of this motor is 30 degrees. You can improve the accuracy to 15 degrees with a small trick. When coil A is energized, the rotor is in this position. We know that when coil B is energized, it moves 30 degrees. What happens when coils A and B are energized together? The rotor will come to a position between these two cases, or it will move 15 degrees. After this, de-energize A. Then, after reaching B, energize C as well. This kind of operation is known as half-stepping.
Okay, so just to kind of fast forward.
Let's understand it first. The rotor becomes the north pole, and the other end.
So
Let's arrange the.
this is just an example with how densely packed these can be. So you probably can't buy, maybe you buy a really cheap stepper motor that only does 15 degrees rotation. That's really coarse. One usually you're talking about on the fraction of a degree for some of these that you can buy. But so when you get this, as a student, you buy this thing and it just works. And they have some sort of software module that controls all the electronic drives. And you plug it in and you say, go to 25.8 degrees and it just goes there, right? The actual electronics are the complicated part. The mechanical part of this is really simple for a stepper motor. But these are great for, they're a little bit more expensive than DC motors, but they're great if you want to be able to control the position of something with high accuracy without any discussion of dynamics of the system. Okay, so they're great for class projects. They're great for a lot of industry applications where you want really precise control or fairly precise control. So as you imagine, you can only get a finite number of positions with the stepper motor. You can't get, you can't get any much better than how good do you buy in terms of your stepper. So they're great for a lot of applications, but the electronics on them are pretty complicated. That's what makes them fairly expensive. Mechanical part is pretty simple for these. So stepper motor, just kind of brief notes. Sophisticated electronics. To step a, basically to step a motor to discrete angular positions. Okay, so this concludes our focus on electrical machines. The whole purpose of this was to get a basic understanding of the physics. How to formulate the equations of motion for these physics. And then lastly, analysis using Laplace transforms. Yes?
For AC synchronous motors, how do you get them started? I think I've used them before, and then they have like a big capacitor on the side.
Yeah, so they have motor starters. So some of them actually have a separate motor that will start them. The other thing too that you can put, where there's basically they stack them also with a bunch of conducting metal, and that does kind of mutes the poles of these, and so allows you to then get them started. So the video, we can go back and watch the video. But I guess if you're really interested in that, you go watch it yourself. But basically, they have ways in which they can somewhat make it like the squirrel cage induction motor. So it's kind of a mix. The ones that actually use in practice use some of the principles of induction motors as well to get them started. And then once it gets going, then it's not an issue. And so the induction motor part of that's still in there, but it's designed not to have much of a response. Yeah, but some of them actually have a separate motor too. Yeah, a weaker motor, right? Yeah. So it wouldn't be the primary mover. Yeah.
Do you have to get it spun up to the like close to the top speed, or
No,
just
just to move a little, yeah.
Okay.
Yeah. Okay. Any other questions before we switch gears considerably here? Make a pretty abrupt transition. Okay, so we don't have time to switch gears a ton here. We're going to start a new module. We'll just barely get into it. So we're going to start a new module. The components, in terms of what type of systems are we looking at, are completely different. But a lot of the math and a lot of the discussions we'll be using are fairly simple, or similar, I mean. Save this. Okay. So we're going to now be talking about fluid power systems, and I wanted to open that with this program. So I'll have time, like 1 minute, to talk about fluid power systems, then we'll get into the course evaluation. Okay, so I think most of you are in fluid mechanics right now, is that correct? Okay, so we're talking about fluid power systems. I would like to say there's a lot of overlap between the two topics in the way we teach it and the way the fluid mechanics class teaches it. If I were to say that the difference is that in fluid mechanics, you're looking at what's happening almost at the molecular level, I would say. And that's an exaggeration, but you're looking at what's happening in terms of fluid slip, you're talking about pressures, you're talking about flow rates. We're going to be talking about the same things, but we're not going to be looking at what is happening at, say, for instance, what is the pressure at a certain location, very specific, so that you can have like, okay, here's the pressure at the tip of this ball that's in the fluid stream, and here's what's on the side. We're not going to be talking about that at all. We're talking about what's called lumped parameter analysis. And so we're going to say we're going to have certain vessels that are a certain pressure, or certain vessels of which we have fluid that's going at a certain flow rate. But we're not going to get down too much into the details of what's happening at every location in the system. We're looking at more broader systems analysis. Your fluid mechanics class is looking at what's happening at each spatial region and trying to understand drag and all those other factors that you may be learning. So it's going to be fundamentally different in the way we analyze this. And it's going to look a lot more like the electromechanical systems that we were talking about, not as much looking like your fluid mechanics class. So same ideas that we have fluid driving systems, but we're not going to be looking at things that you care about, for instance, looking at profiles of flow in a pipe, et cetera, that you may be doing in your fluid mechanics class. Okay. In the last minute before we hand out evaluations, the main idea or the importance of fluid power systems, the advantage is all based off of basically the principle, which you would have seen in your fluid mechanics class, is that by I can very easily in fluid power systems distribute power, right? So if I look at my electromechanical systems, if I want power delivered to a certain location, I have to run cables there, and then I have to have a motor at that location, right? Or some sort of driving element at that location to apply power. Fluid power systems are nice in that they distribute power everywhere, in a sense. So if I push down on this piston, I can have some pretty irregular vessel, and it's going to create pressure everywhere normal to this wall. And what that allows me to do is I can actually use that for work. Okay, so oftentimes we have, at the end of a line, we have some sort of power element, fluid power element, say for instance like a calipers on your brake system in your car. But also we can use this to distribute power everywhere along a wall, etc., to do work with. Okay. That's it. That's all we're going to learn about fluid power. I'm kidding. We'll talk more about this on Friday. But that was like the main taste.